In this video, we're going to look at two ways to implement a list. Okay, so one way is we could use an array. And if we use an array to implement a list, we're just gonna, allocate a block of memory, store the list items in the array, and then manipulate where they are in the array when we need to perform an append or a removal or an insertion or any of these operations we want to do on a list data type. Or we can use a linked list. And a linked list is different from an array in that each of the nodes in the list are connected using pointers rather than being laid out contiguously in memory. And so these are two approaches. For the array, hopefully you can kind of imagine what that implementation would be like. For a linked list, I'm hoping that you've seen this once before in EC 209, and so this is will be somewhat of a review when we get into those details. But I am going to go into a lot of detail for how the linked list works. Okay, so for the array list, let's just sketch this out really quickly. I think that you can fill in a lot of the details on your own. You could probably build an object that works this way if you were, tasked to do so. And so I'm just going to sketch out some of the features of an array-based list. And with the caveat that it's not going to be a very efficient implementation and that you could definitely make it more efficient. And we'll talk about some ways you could make it more efficient as we go. And we'll also see some such implementations later on in the semester. Okay, so if we had an array, then we might create a class that looks something like this. And this just gives us a little more of concrete context in which to discuss. So I might make a class called ArrayList, and then I would declare a few member functions like append, then remove, and empty. And let's say that this array list is purely working on integers, though it could be anything. We just need to change those types that we're passing in and getting out of it. Okay, so in our constructor for such an array list, we might just directly allocate an array of integers. And since we don't know how many integers will be in our list, one strategy would be to just pick a really big size and make a really big array. I'll argue that 1,000 is big for a lot of uses of a list. And so maybe that would be big enough. Maybe it wouldn't be. And then maybe we'd have another integer variable, member variable called head that would simply point to the next free and available location in the list. And so in this case, since we have nothing in our list at the beginning when we're constructing this object, we'd set head equal to 0 to imply there's nothing in the list. And this also implies how we would check if the list is empty. If head is equal to 0, the list is empty. If head is not 0, then there is, or greater than 0, then there is something in the list. Right, so how would we check if it's empty? We just check if head is equal to 0. Okay, how do we append to the array? Well, what we would do is in the location of the array specified by head, we would store our new item, whatever that item is, an integer in this case. And then we'd need to increment head afterwards. So I'm using this postfix increment. You don't have to do it this way. Just after this statement, you could add 1 to head. And that would move head down 1 position in the list, letting us know that we've added something into the list. Now, there is a little case here that you should worry about. What if, after you increment head, it exceeds the array size? We know it would be bad to try to access memory beyond the amount that we had previously requested. And so we need to detect this case and allocate a bigger array. But I'm not going to show that. I'm just going to assume for now that we stay within the confines of that array we created. It's big enough, it tends to work. But there are these other cases you would have to build into your code for this to be a really, well-functioning array list. It would not be acceptable for you to exceed the bounds of the array. Okay, and then what if we wanted to say remove the item at the front of the list? Well, a really naive way we could do this would be to kind of remember the item that's currently at the front in position 0 And then we have a loop that just shifts everything down. So everything that's, say, the thing at position 1 gets copied over to position 0, and then the thing at position 2 gets copied over to position 1. And we go all the way down the array up till the head and move stuff down 1, okay? And then after we've done all of that, we subtract 1 from head to indicate we have 1 fewer things in our array list than we had before. This is for the particular case of removing something from the front of the list. If we were removing something from somewhere else in the list, the process would be a little bit different. And then let's say we had an operation where we wanted to insert into the middle of the list. Then what we might do is specify it as, I want to insert value X after Y. And so we would need to find the matching value, and we would do that by scanning across the array until we find the matching value Y. And then we shift all the values that come past it down 1 location in the array to make room, and then we can stick X in the list there. This also would require us moving head by 1 to indicate that we have 1 more thing in the list. Okay, so that would be the sort of implementation for insertion on my array list. So let's just briefly talk about the complexity of these operations. Hopefully you've read the Zybook chapter on Big O. It should be a review from content you've seen before in the discrete math class. So if we look at how expensive these operations are to perform on our array list, then when we append to the tail, all we have to do is store a value in the array and increment the head by 1. Those are both single operations, and it doesn't need a loop or anything like that. And so that's O1. We can do it in constant time. Removing from the head, this was a little more complicated, right? We needed to shift all the elements in the array down by 1. That means we needed a loop, and we needed to visit every entry in the array and move it. And so that would be order n, because for the n elements in the list, we might have to touch each one to do that operation. So that's expensive. That's an expensive operation. Now, I will note that if we were clever, we could actually do it in O1. The key idea would be, just instead of only having a head pointer, let's have a tail pointer as well, and remember both ends of the array. And then we don't need to shift everything to the front of the array. We can just keep track of exactly where in the array we're storing our information. So that would be a trick we could use to make it much more efficient. So it can be more efficient, but that particular implementation we just wrote is ON. To check if it's empty or not, we just have to check if the head is null and or 0. And then for insertion, we have to find the place where we're going to insert, and then we have to shift everything down. Now, this turns out to be ON again, because in the worst case, we're going to insert at the front of the list, and we have to move everything in the list down 1. Okay, and that's a very expensive operation as well. That's order n. Okay, so this array list we just implemented is has some efficient operations like adding to the tail or checking if it's empty, but it has some inefficient ones like insertion and removal from the head. Now you may say, well, order n isn't that bad. If I have n things in my list, maybe it's not so bad that it takes me n steps to figure out what to do. Well, that's true. Order n isn't as bad as order n squared or as order 2 to the n, right? Those would be way worse. But if we can have constant time operations, that's what we want, because these data structures might be things we use a lot in our code. And so anytime we touch the data structure, we want to be able to utilize it as efficiently as possible. So we're really striving for O1. And really in general, anything in computing, if you can do it in O1, that's what you want. If you can be creative and come up with a constant time approach, that's ideal. Okay, so in summary, the list data type can be implemented using an array. A key limitation of this array implementation is that insertion in the middle of an array or at the beginning of an array is expensive. It's order n, which is not good. Ideally, we want order 1, big O of 1. So can we have an order 1 insertion using a different implementation for a list? That's a question. And the answer is we can. If we use a linked list instead, we can have order 1 insertion. And we're going to take a look at that next.